Here's a conundrum. One stair tread here sits on the ground and is built into a very thin wall. The next tread sits on top of it, and it too is nominally built into the same wall. The thing is, if you stand on that tread, how does it not collapse? Keep adding steps and still the structural system is always stable. This programme takes a look at the loads, the torsional shear forces, but not too many calculations. Stairs with no visible means of support, stairs that logically surely shouldn't stand up, are a fascinating architectural and engineering trick. We asked Steve Webb of Webb Yates Engineers to talk us through the secrets and the physics of self-supporting stairs.
So the principle of a stone staircase is that one unit sits on top of another unit. They're built into a wall on the far side and prevented from twisting, and they're free on the inside face of the staircase, which can either be a square block like that or a cut, tapered tread. The structural principle behind the way it works is that this tread, for example, is supported there on the front edge and in the back corner behind and held down in the front so that the end can't twist, which means that this corner on that step is now structurally stable, which means that you can put a subsequent unit on top of that in exactly the same way and continue to build one on top of the other. The only limiting factor is the strength of the stone in torsion, that if you continue to build the stair for too long, you have such an enormous amount of force travelling down through the treads that you can shear off an individual piece. So we thought this principle was very interesting, and it defies or appears to defy gravity in some sense, and people don't conceive of the way that the item is working as a structure, even though it's fully unclothed and exposed to the eye. So the first time that we used it, staircase in Valencia in Spain, was with plywood. So I think we do exactly the same thing as the stone blocks, one on top of the other. A hollow plywood box will behave in exactly the same way as a stone block will. It has a lot of torsional resistance because it's hollow and the ends are filled in. In this instance, it was a staircase up a 2-meter flight to a sleeping slot above a bedroom. And the wall that was supporting it was a typical European internal partition hollow terracotta wall, 50 millimeters thick, and the terracotta tiles that formed the wall were probably only about 5 millimeters. The wall thickness was 5 millimeters, and then there was plaster on the outside. So we literally built a series of plywood boxes, one sat on top of the other, with wood screws and wall plugs into the terracotta. So there's absolutely no way that incredibly thin and incredibly weak wall can support a cantilever of that magnitude with somebody as heavy as I am jumping up and down on the end of it. The staircase doesn't have any kind of head restraint, and in actual fact stone staircases, because one stone is laid on top of the other, rely on the treads beneath the load supporting them predominantly. There's a secondary torsional restraint by a horizontal support at the top, but it's not necessary for the stability of the stair. And you could extend this principle, not necessarily for a staircase, but you could build these boxes outwards. You could build canopies or other things, but actually the most useful thing to build with it is a staircase. So you can see there how those project. It's a very simple thing. It's nice looking, and it's very easy to construct. The second staircase we built on that principle, we started thinking, well, actually the torsional capacity of the box needs to be at the far end, and it's less loaded at the pointy end. So we started to taper the boxes and to cut away the unstressed sections on the outward projections of the boxes, and remove material and depth from the sections that are least stressed. So the torsions are more concentrated on the wall, and you need the depth on the wall to achieve the level of torsional restraint, but you don't need it on the tip of the staircase. And by cutting it out, you can effectively create a much lighter stair, or a stair that has more in common with a more typical architectural cantilevered staircase that relies on a encaster support at the wall. So in this instance, the client was using laser cutting to cut plywood to make architectural models for that practice. And so he was telling us that we should, that we could create the staircase by laser cutting each of the components by making a site measure. And so all of these elements were completely prefabricated. Laser cutting a sheet of ply costs 250 or 300 pounds, and getting all of these pieces delivered and screwing them together is a very quick and very easy process. So this is a time-lapse photograph of the client and his friend building the staircase in the course of one day, I believe, bolting the plates that the staircase takes support from onto the wall. The wall's a brickwork party wall, so it has very little integrity. You couldn't justify it to support a cantilever from. You can only justify it to support torsional loads in its own plane. So then we started getting more interesting projects, or I should say higher budget projects. And in this instance, the idea was to use a solid oak bat rather than a plywood stair. So this is a much more expensive version. It's in somebody who works in the financial sector's news house in Notting Hill. But the principles were ostensibly the same. It had winders, so you end up with quite a nice detail as the winders trip around the corner to the upper level, and then the lower section, the balustrade supports are completely separate from the staircase. The wall that's supporting the stair is a plywood studwork wall with stainless steel pins connecting the treads into it. So again, it's kind of easy to erect, and and it's kind of it's got all the appearance of a staircase that projects out of the wall without all of the heavy steel work and engineering that those staircases normally entail in burying an square hollow section in the masonry or in the stud wall. Each tread is supported on the plywood lined stud wall with two stainless steel pins. The torsion that we were resisting in the earlier staircases through it either being built into the staircase or having multiple screws or bolts is resisted by the two stainless steel pins acting as a fork embedded in a plywood wall. So these treads at the top have two pins, that one has two pins, that one has two pins, all the way down the staircase. In a lightweight timber stair, the self-weight of the treads themselves isn't very significant, so there's a very light accumulation of load as you travel down the stair. Most of the load, or most of the torsion that the staircase is resisting, is from people standing on it. If it were a stone stair, the load accumulates much more quickly because of dead load, and the stresses on the bottom tread are far higher than the ones on the top tread or the penultimate bottom tread. In this instance, the critical factor was that the stainless steel pins were epoxied into the oak bats. If you follow the code, the edge distances between the pins and the timber that's surrounding them are too small, but that's for a normal dry bolted connection. If you epoxy the bolts in, then the epoxy tends to bind the timber around the pin together and prevents the pin from bursting out of the timber as easily as it would if it were dry or just threaded into the wood. So in this case, there's no codification of epoxy pins in the end grain of oak under shear and torsion loads. So we made up a test which involved a couple of people jumping up and down on the first three treads to be built in order to guarantee that it was performing the way it was supposed to perform. So there was a small risk in the staircase for the client, but he was happy to accept it, and actually we felt that an epoxied pin in an oak tread would be much stronger than the code would actually suggest. So the final staircase in the timber series of these stairs is in a house in Earl's Court. In this instance, the treads are formed with multiple layers of plywood that are all laser cut. Actually, there are some voids cut in them to reduce the weight, but in general, they're it's very much like a stereolithographic model in the sense that you're just cutting out lots of sheets of ply to make this form. These are screwed to a curved plywood baluster and separated from the wall. Actually, it's got 2 pins into the wall to prevent instability on the entire staircase, but it's the same principle. In this instance, though, instead of having a masonry wall on the outside of the staircase or on one side of the staircase, we have a plywood or a curved plywood baluster or balustrade that has a lot of stiffness in that direction and can behave in exactly the same way as a wall would behave in the normal instance. At the same time, well, it has a lot of stiffness because it's supported by the treads. So there's a sort of interdependency of the two items, but the principles for the treads themselves are exactly the same, that each tread sits on top of the other and that there's a gap at the side of there and no stringer. Through doing these timber staircases, we were asked whether we could actually do the analysis and the calculation for a stone staircase of the same design, which is very interesting that our cheap alteration on the rather posh stone staircase resulted in us getting projects for actual stone staircases. So this is the first stone staircase that we've done. This is built into a masonry wall. It's a classic example of one of these stairs, quite thin sections on the internal edge, and we were using solid FE modelling to assess the torsions in the treads, so this was a successful job. We worked with a very good French stonemason who's been building these staircases for some time, and hadn't been asked for calculations before, which is why he came to us for some justifying calcs for his stair. So we did a few staircases like this. This one's built into a blockwork wall. And then we started thinking about, through using the stone, other variants or other developments that you could make with a stair of this sort with stonework. So we came across one project which was in Holland Park, where they wanted a freestanding stone stair. And we came up with the idea of post-tensioning the stone, post-tensioning one side of the treads to form effectively the wall or an internal stringer on the staircase, and using effectively a similar principle to cantilever the treads off the side of the post-tension portion of the flight. The architect was very keen to maintain the shallowness of the internal edge of the staircase because the staircase connected onto a visible balcony edge which sat on the back of a building. So the inside edge of the staircase is 50 millimeters thick, and the inside edge of the balcony that it joins is also 50 millimeters thick. On the opposite side, there's a consistent waist thickness of about 60 millimeters. And what we've done is to scallop out the treads progressively as you rise up the staircase to create effectively a flying carpet edge on one side and then a more typical staircase edge on the other side. So this is a model of the stair, and this is showing the tendons that run through the stonework. Reinforced concrete and post-tension stone are very similar in their engineering principles, in that the stone prevents or resists tensions that are imposed on a global composite section. However, stone is often much stronger than concrete, and concrete suffers from creep and shrinkage, whereas stone doesn't, because it's been in the ground for however long. And so you can actually get out of a reinforced stone section much better performance, much shallower depths, stronger sections than you can out of reinforced concrete. And so we're able to make the staircase very, very thin, and the tendons run. You can see the way that the tendons fan out across the widening section of the staircase. The staircase is built, or in fact it was built on a blockwork wall for support, the cables were exposed on that edge of that tread and then post-tensioned using a post-tensioning jack to 75 kilonewtons each, about 7.5 tons in each cable, so 15 tons of tension resisted by the stone on the staircase. We did have some problems because the tolerance between each tread needs to be very, very tight for you not to actually break the treads. So we broke a few treads by not having the intersection between the tread below and the tread above accurate enough. And in the end, we used a mortar bed, a high-strength mortar bed to prevent that from happening. Wall staircases are interesting for structural engineers because they're completely exposed, or frequently completely exposed and undecorated. And so quite frequently what you see in a staircase is what it really is, rather than something with a plasterboard ceiling or whatever. And there's also, I think, an enormous movement for people to show off with their staircases. It's the palanquin of, the bespoke palanquin of the modern world. So there's a lot of opportunity to experiment. There's a lot of opportunity to experiment with materials and with analysis, and to really show off how clever you are at analysing and conceiving of structural systems that other people don't necessarily think of. There's a website.